Well, hello. This is John Perham here, and I'm going to work out the solutions of the problems in the second test for MATH2019, and there were two sets of problems, which I'll call the yellow problems and the blue problems. So we'll start with the yellow problems. So the first problem is about a differential equation, which we can establish using that. And you can see it's a second order linear differential equation with constant coefficients, and it has a forcing term here. So the problem is, well, the problem we're asked to solve is find the homogeneous solution, which is the bit without the forcing term, and find for which value of omega the solution will exhibit resonance. So let's get on with that. So we'll open the solution up. We can easily get the homogeneous differential equation by setting the frequency in the forcing term to be 0. So there it is. And the way we solve these is we assume that there's an exponential solution, like so, and then we differentiate that twice with respect to t to get that, and then we put all that into the differential equation and obtain an equation for lambda. Well, a can't be 0 because that would just give us the 0 solution. E to the lambda t is never 0, so we conclude that the values of lambda are the solution of that, and we can find those. And we can see that they're both imaginary, which indicates that the solutions will be oscillatory and thus a linear combination of the cosine of 3t and the sine of 3t. So there it is. Well, when will it resonate? Well, it'll resonate basically when the frequency of the forcing term, 2 pi omega t, is equal to the frequency, 2 pi omega is equal to the frequency of the homogeneous system, and that will occur when that frequency is 3 divided by 2 pi. So that's the solution to the first problem. Here's the second problem. So we've given this substitution, and we're asked to use that to find the general solution of this differential equation. So let's do that. First of all, we want to establish the differential equation, which I can do using that. And you can see that I've made y a function of x. And now the transformation to the new variable is given by this, or satisfies this equation, and we can solve that to express y as a function of v, like so. And we can also, well, we need to differentiate that, so we can do that like so. And we'll also need the reverse transformation at some stage, so we solve that equation for v as a function of y. Well, we now want to get the differential equation for v, which we can do by substituting the transformation and its derivative into the equation, which is here somewhere. There. So let's do that. And what do we find? Well, let's simplify it a bit to see if there's anything we can do. Well, if we look at this, we can see that the differential equation is x squared, which we can cancel out because it's equal to 0, and we can see that this term here only depends on v, and x is a factor of this term. So this equation is separable, and I've separated it manually. So I've divided by this and by x. So that's what the differential equation, or that's the separated form. And now we can integrate this because the top here is proportional to the derivative of the bottom, and we know how to integrate 1 on x. So let's do that, and that will give us what's called an implicit solution. And we could set that equal to 0 and solve for v using that, and we'll get 2 solutions. And then finally we want to find the solution for y, and we can do that by applying the reverse transformation. Well, whichever one of these solutions is relevant will depend on where we start, but this is the general solution. So that's the solution to that problem.